Okay, so moving right along, let's take those skills that we learned in the last video and try to graph some of these functions. And then later, when we're given a graph, let's see if we can't come up with that equation. So in these first three here, it says to list the transformations in order, state the domain and range, and then graph. So for example 1 there, x plus 5 squared minus 3, I think we would all agree that the transformations in order are, because of that plus 5 inside, left 5, and then that minus 3 down 3. This square is kind of giving us a clue as to what the parent function is. So the parent function for this thing is x squared. And usually when I'm graphing transformations, I will first identify the parent function. So I'll just kind of write down to the side, or at least in my head, say, okay, the parent function for this thing is x squared. And then the second thing I would do is list my transformations in order, so left 5, down 3. And with this, we can graph. Okay? We know what the function looks like originally because we know what x squared looks like. And I can take that original function, move it according to the transformations, and then be done. So I'll go a little slow here, but I think we could all, at least, and some of you will be able to do this in your heads, but all of you know what x squared looks like. Y equals x squared. Whoops. Okay. This is y equals x squared. Okay. So this was the parent function. This is what that thing used to look like. So what does it look like now? Well, it's been moved left 5, down 3. So I can take every point that I know was on the original function, move them left 5. So for example, maybe I start here. If I go left 5, 1, 2, 3, 4, 5, down 3, 1, 2, 3, it would be here. So this point on the original function gets moved here under these transformations. Maybe this point. If I start at this point, which I know, again, is on the graph of my parent function, if I move it left 5, 2, 3, 4, 5, down 3, 1, 2, 3, we get here. And then you could do that for some other points. If you did it for this point, you'd get here. Maybe we do it for this point very quickly. Left 5, 1, 2, 3, 4, 5, down 3, 1, 2, 3, and we'd get here. And if you did it for this point, you'd get here. And so we have the graph of our function. Here. So this graph in red is what the graph of f of x looks like. Cool. The original function moved left 5, down 3. Not bad. Well, I think we would all agree that number 2 looks quite a bit more intimidating than the first one, but it's still the same process. We would identify, let's real quick, just because the directions say, let's identify the domain and range of that function. So the function in red is what we're talking about here, this function. So what's the domain of this function? And this function has a domain of all real numbers. It goes forever to the left and forever to the right with no breaks in the middle. So as far as our x values are concerned, left and right, the domain is from negative infinity to infinity. The range of this function are y values from bottom to top. What's the lowest to the highest? Well, the lowest y value is actually here at negative 3. Negative 3 is the lowest that red function goes, and then it just goes up forever. So from the lowest point of negative 3 up to infinity. Cool. What about the second function? Well, if we follow our kind of rules, we would identify the parent function, which is, again, y equals x squared, because that's the operation being done to the x. And then our transformations in order, what do we got? Maybe right 2, looks like there's a reflection over the x-axis. There's a vertical stretch by a factor of 3. I'm excited to see what that does. And then up 4. So those would be our transformations in order. Okay, so let's imagine what's going to go on here. Again, some of you already have these points memorized, but maybe the first thing you do is imagine what the parent function looked like. Okay. So we know for sure the function used to look like this, for sure. Okay. But we're going to take these points that we know are on the graph of our parent function and move them all right 2, reflect them, stretch them vertically by a factor of 3, and go up 4. Okay. So there's actually going to be quite a lot going on with these points, but as long as we're careful and we take our time, this shouldn't be too big of a deal. So let's maybe start with this point. If I start here at 0, 0, I'm going to do quite a lot of work here, so maybe you'll follow along. I'm going to take this point and move it right 2. 1, 2. That puts me right here. Okay. Next, I'm going to reflect over the x-axis. Well, right off the bat, there's kind of a tricky one, but this is already on the x-axis, this point here. Is already on the x-axis, so when I reflect it over the x-axis, nothing changes. So when I go right 2, reflecting over the x-axis, nothing changes. Vertically stretch by a factor of 3. To stretch something vertically by a factor of 3 means to take that point's current y value, so what's the current y value of this problem, or this point, and that current y value is 0, right? Here's a y value of -5, -3, +4. Here, at the point that we're worrying about, is a y value of 0. And 0 times 3 is still a y value of 0. And then the last thing would be to move it up 4. 1, 2, 3, 4. It would land me right here. Okay. Again, very quickly, we went right 2. We reflected over the x-axis. Nothing happened. We multiplied the y value, which was 0, by 3, and 0 times 3 was still 0, so nothing happened. And then we moved it up 4 and got here. Okay, so kind of a tricky point to start with, but let's do another one. Let's do this point. Okay, I'm going to move it right 2, 1, 2. It's going to put me here. Put a little marker. Okay, I'm going to reflect it over the x-axis. So over the x-axis. Remember, the horizontal axis is the x-axis. So if I reflect this point over the x-axis, it used to be 1 above the x-axis, so when I reflect, it will be 1 below the x-axis. So now we're at this point. Okay? Now what? Now we're going to stretch vertically by a factor of 3. So what does that mean? It means to take the y value that you're currently at. In this case, look, the y value of this point is -1. Remember, here's -5, here's 0. The y value of this point is -1. And -1 times 3 is -3. So I move that y value to -3. And then I would move up 4 from there. 1, 2, 3, 4. Okay. Whoa. So a lot went on there, but we went right to and landed here. We reflected over the x-axis and landed here. We multiplied our y values by 3. -1 times 3 was -3, so we took it down here to that y value of -3, and then we moved everything up 4. 1, 2, 3, 4. And that's how we landed here. Okay. I'll let you transform this point, but you'll actually land right here, and we're going to get a graph that so far looks like this. Weird, I know, but if you take this point here and go through that process of moving it right to, reflecting it, vertical stretch up, you land right here. Okay, so this point gets moved here. Okay, And then the last one we'll do is this point right here. Let's transform it. So I would move right 2, 1, 2, and that would put me here. I would reflect over the x-axis, so currently I'm 4 above the x-axis, so when I reflect I'll be 4 below. I would stretch vertically by a factor of 3, so I would take the y value of this point and multiply it by 3. Currently this is at a y value of -4. -4 times 3 is -12. But then if I move it up 4, if I'm way down here at -12 currently and I move up 4, I get up to -8. And that's what that function looks like. Okay, that's a pretty tough one. We may on a bigger whiteboard or something in our live sessions do another example like that because it's kind of hard to see with how small everything is, but that's what that's going to look like. Real quick, the domain and the range here. The domain is all real numbers. And the range is from low to high. So if we look at that red function, from -infinity to stops here at a height of 4. So from -infinity to +4 is our range. Great. Let's save example 3 for the live sessions, but just kind of in your head, take a second and see if you couldn't identify at least how this thing moves and what the parent function is. Okay. All right. And then we'll do this example together and we'll save the square root, well, spoilers, we'll save this unknown function for the live sessions. And we'll probably save this absolute value stuff for the live sessions as well. Okay, so last example here, let's kind of work backwards. In the previous couple examples, we were given a formula and asked to come up with the graph. In this, we're given the graph and asked to come up with a formula. So identify the transformations and write an equation. Well, the first thing I'm going to notice is that the parent function that this thing is based off of is the quadratic. So we're definitely talking about something squared, so it should look like maybe one of these formulas. But it definitely doesn't look like our parent function. Our parent function goes through the origin, through 1, 1. Our parent function looks like this. So what transformations has this original parent function undergone to end up looking like this? Well, there's a few things that have happened, so let's try and see if we can't find them and then list them in order. I think we would all agree that this whole function got moved left. How far left? Well, 1, 2, 3, 4. If that whole thing got moved left 4, it might end up looking like that. Okay, so there's definitely a left 4 in the mix. The next question is what happened next? And please remember the order of these transformations. Some people might get going real fast and say, oh, next it got moved down 2 and then reflected. But remember, going down is the last thing we do. So it actually got reflected, it got reflected first and then moved down. That was awful, sorry. Reflected first and then moved down, okay? So if this thing gets reflected over the x-axis, then it might end up looking like this. So it definitely got reflected over the x-axis, and then I hope we all agree that it then got moved down 2. Okay? So from the original here, we moved it left 4, and that's how we ended up here. We reflected over the x-axis, that's how we ended up here. And then we moved the whole thing down 2, and that's how we ended up here. So all in all, our quadratic with these transformations. What's that equation? It's definitely y equals something. But what's that equation? Well, let's tackle the easy part. What's that down 2 do? Hope you said out loud. There's going to be a minus 2 at the end. There's a reflection over the x-axis, so automatically I know that there's like a negative in front. And then there's this left 4. But so that, I hope you agree, means there's an x plus 4 somewhere in this. Left 4, x plus 4. But where? Well, it's going to be inside the parent function. So the parent function is x squared. So there's going to be that x plus 4 on the inside of the parent function. Remember, because that left and right stuff occurs on the inside of those functions. And so there's our equation. If you type in your calculator negative parentheses x plus 4 squared minus 2, you will get this image. Pretty cool. So from a graph, we can come up with its equation because we know what the parent function looks like. It was a quadratic for sure, and we know how to identify its transformations and what those mean in terms of the formula. Awesome.